Hi, my name is Paige Seifert. I'm a sophomore in mechanical engineering at the Colorado School of Mines in Golden, Colorado. I've always enjoyed mountain biking, and a lot of my friends at this school do too. But a common topic of debate is suspension pressure and what your pressure should be based on your weight. I've read a lot of mountain biking forums, and it seems like a lot of other riders struggle with this too. So I've taken my passion for mountain biking and my passion for programming and created a MATLAB program that gives a rider the recommended pressure based on their weight. Here's how it works.
The program uses the menu function to ask for the rider's suspension type. The program then distinguishes between two suspension types. For fork suspension, the program uses an input function to request the rider type in their weight. I've inputted the weights and recommended pressures provided by SRAM RockShox suspension chart. The program then uses if and else if statements to decide the recommended pressure and displays it for the rider. For the rear suspension choice, the program uses an input statement for the rider's weight and adds 40 as recommended by RockShox and displays it for the rider. Here's a 130-pound rider. The program says that the fork should be 55 to 65 psi and the rear suspension should be 170 psi. Here's a 110-pound rider. The program says that the fork should be 55 or less psi and the rear suspension should be 140 psi. When the suspension is pumped to the proper pressure, it produces the perfect 30% sag as recommended by SRAM RockShox. Here's the whole system in action.
So you may be wondering, why is suspension so important? Well, let's talk about the physics of suspension. Here I've drawn a free body diagram of a bike with no suspension. You'll see it has normal force where the wheels make contact with the ground, and then there's the force of the rider, which is their weight times the force of gravity. Alright, so why is that important? Let's make this diagram mean something. So we can draw sum of forces in the y direction equal to 0, where mass times gravity is the force of the rider. We know that we have two normal forces pointing in the upward direction and the force of the rider pointing in the down direction. We solve this all out using algebra, and we find that the normal force, which is the force pushing back up on the rider and on the bike, to be the mass times gravity divided by 2. So this is the equation for the force felt by someone riding on a bike with no suspension. Now it's not this simple. The body is still going to have a natural tendency to absorb blows through bending of arms and legs. But generally, a bike with no suspension is going to feel a lot more jarring ride compared to that of a full suspension, because that natural tendency is still going to exist when you're riding a full suspension bike. Now let's talk about how the suspension on a full suspension bike works. So there are air shocks and there are coil shocks, but for this scenario in this project, we're really just talking about air shocks, but they are fundamentally the same. The suspension is a cylinder full of air, which compresses when the bike is under load. For example, when a rider rides over a bump, the suspension is going to compress, and when it's over the bump, it's going to then extend back to its normal form again. So here's some suspension diagrams which represent the suspension under load, where the length of the arrow represents the magnitude of the force. On this side, we have a suspension under no loading, and over here with these two, you can see how an increase in force results in an increase in air pressure. Alright, let's check out this code on the trails.
Yeah,
Woo!
just out hit shot.